Yeah. So what we have discussed in the last class?
The different deformation processing systems and the categories of them based on the forces applied. Then we saw about the strain, and we derived the equations for conventional strain and true strain. Then we also derived the formula for reduction. Then we did numericals.
Yeah, yeah. Okay, okay, fine. So all the students you have to because you know the up to the last class I have already uploaded. So maybe today or maybe one more class I need after this class. So I will compile everything. Then I will again upload the final version. Okay. So in the last class also we have talked about Charles told that the types of forming operation depending upon the forces applied. For example, the direct compression type. Then we talked about the indirect compression type, then shearing, then also tension, then also bending. Okay, so these are all we covered. Then also I put one schematic diagram. If you remember, we talked about the deformation system, how the undeformed metal piece or the sheet, then it is going towards the deformation zone. So what are the parameters you are looking there for the tools or the die? Then also you are applying the force there, then heat generating, then also the friction, then also the lubrication system, and you are getting the final product, whether this is forced or maybe rolled, you are getting. Then we talked about the mechanics of metal working, so we derived some equations. Then based on that, we have done some numerical. Then also finally we have talked about the different kind of analysis method, because you cannot stick on only one method. For example, the what we talked about, the finite element method, I didn't go in detail because not required. If you are much more interested, then you can go, you can follow the detour book so that you can find. Then also we talked about the uniform deformation energy method, then upper and lower bound solution, slab method. These are all we have discussed, right? So today we will discuss on the effect of heat treatment after the cold working. So these are the mechanism. I think probably we are not going so deeply, but little you have to understand. We understood the effect of temperature, the cold working, hot working, warm working. But here we want to discuss a little deeply about the mechanism again. So whenever we are talking about the heat treatment, because you are removing the internal stresses. So here there are three annealing stages we have. So one is recovery, then second one is recrystallization, and third one we have the grain growth. So here I mentioned, and somebody will ask you why actually we want to go for a recovery or recrystallization or grain growth, because whenever you are doing something, there should be some logic, because due to that only we are going. For example, I told maybe in the previous composite or maybe somewhere we have a lot of techniques, but you do not think that this technique is totally wrong or bad. That's why we are going to another. Probably we are finding some deficiency there or some limitations there. So that's why to overcome that one, we are going for another process, right? So here also the recovery, recrystallization, and ground growth. These are the microstructural changes, because whenever you will see the microstructure or the morphology of the material or the product what you are getting. So these are normally we are finding in the steps of recovery, recrystallization, and grain growth that occur during the annealing after cold plastic deformation and or during the hot working. Okay, so I put two schematic diagram here. So this one, the right hand side, you can find this is at least you have to understand the basics how actually it is happening. Okay, so this is a schematic one. Maybe when you will do the lot of experiment with different kind of material, so you will find a little bit of deviation there. Okay, so if you have the product here, sorry, the raw material here or the hot rolled sheet, what you are putting here inside the this testing method or the equipment, and this is normally the example they have taken of the wrought product or the wrought iron, right? So here when you are pressing or when you are using with the help of any kind of metal working technique, so that means your grains, whatever the grains you have here, the particle size or maybe the grains, and these are, it will elongated because you are pressing here. So that means you are applying some force here, right? Because two rolls are there. Let's say you are talking and this is rolling, so that means two rolls are there, right? So the moment you are applying pressure here or you are giving the pressure here, so that the grains, it will be elongated because you are squeezing, you are pressing. Okay, so the moment this deformed elongated grains are there, then after some time you will find little gap there. Little gap means from that elongated again you will find some new grains there. Okay, so you can just imagine some kind of like the bubbles when the like the foams we are putting inside the like for kids normally we are giving inside a tube there are some foam liquid are there, but when we are putting or when we are giving to the outside atmosphere, how this is separating from one big bubble to small bubbles, right? So again, after these new grains or the deformed elongated grains, then you are finding some small grains you can see here. Small grains. These are again new grains are generating there. Okay. After that, then again you are finding some big grains or maybe the the recrystallization complete what we can say. Okay. So if you go to the previous photo or the previous diagram in the left hand side, whatever I put here. So three things I mentioned here. So one is this left hand side. This is known as the recovery part, and the middle side, middle part. This is recrystallization, and the third part. This is grain growth. So you can see here. This part I have taken here from the when this deformed elongated grains. So here this is the maybe please mute. Maybe somebody is Sankara, please mute. Yeah, okay, fine. Okay, so the first part I mentioned, is it clear what I'm talking? Am I audible, right?
Yes, sir.
Okay.
Yes, sir.
So the first part I mentioned here, this is recovery, because three things we just want to combine in one graph so that it will be better to understand. So the first part we mentioned here, this is recovery, and the middle part, this is recrystallization, and the third part is grain growth. So how you can see, this is the elongated part. Okay, so this part, whatever I put in the red graph right hand side, then you are finding or you are creating some new grains there, small grains you have. Then again it is little increasing. Okay, so you will find this kind of grains. Then automatically when it is going towards grain growth, so that means the grain is already growth, that one. So that after that you cannot make it enlarge or make it bigger. So when you can see in the recovery, if you go to the upper side of graph, so your strength, the green one, this is strength, and the black one, this is hardness, and the red one, this is ductility. So the strength is a little in the higher hand side, the strength and the hardness. But the moment this is changing to recovery to recrystallization, and the strength and the hardness both are going downwards. Okay, then when it is grain growth, so that means this is almost there is no change. But it will be, of course, if you compare from the recovery, it will decrease. Similarly, when ductility, in case of the recovery, this is in the lower side. Then when it is going towards the recrystallization and grain growth, this is automatically or this is going towards the higher hand side. And if somebody will ask you why the hardness actually this is decreasing, can somebody tell why the hardness is decreasing when you are going towards the recrystallization and grain growth? Just guess. Anyone? Or the strength, for example, the strength is decreasing. Anyone?
Sir, if the grain size increases, strength decreases.
Yeah, this is okay. But any other common statement? If the grain size will increase, of course, the both will decrease. But any other point?
There might be some micro cracks.
Might be. Before that, you told might be soft.
There's some micro cracks.
Okay, micro crack. No. Micro crack. Why you will find micro crack?
When stretching out the strain.
No. Because for example, if you do not have any micro crack, then any relate to temperature, because we have studied. Because whenever you are increasing the temperature, so what will happen? Your material will be
Hard,
softer.
sir.
Soft, na? It will be soft.
Sorry,
Like the blacksmith, what they are doing? They are increasing temperature, then the metal will be softer, then they are forging or they are hammering. Then it will change, right?
Yes,
Yeah?
sir.
Okay, so when you are increasing the temperatures, your material will be soft. The moment your material will be soft, your the product will be low strength or the hardness also strength. Then after solidification, that will be different. Just we are talking about the softness of the material because you are increasing the temperature. You are going towards annealing, right? Is it fine? Okay. Yeah. So just I put again in a different way, the basic background of the heat treatment, what we are doing here. So I mentioned some of the points because maybe you remember you studied a long time back, maybe in your first year, I think, the annealing. So I mentioned here the plastic deformation, the temperature range, 0.3 to 0.5 melting temperature. Normally these are, we are calling the cold working. We have already discussed in the previous classes. Then the point defects and the dislocation have strain energy associated with them. So I'm not going towards in detail of the point defect, then the dislocation, then the lattice structure. These are we are not going, because you have to understand that there will be some strain inside, because we have to remove that one. Okay, and 1 to 10% of the energy expanded in plastic deformation is stored in the form of strain energy. That is, the material becomes a battery of energy. Okay, so I put in a different perspective, because only just when we are studying in one line, or actually we are talking about, but these are normally when we are talking like the source of energy. Okay, so we are considering the battery. So I just correlate to that one, because inside, if this energy you are storing there, so that means this is the source of energy you have. And the cold work material is in microstructural metastable stage, and depending upon the severity of the cold work, the dislocation density can increase. Okay, so whatever the dislocation you have inside, because in the last class we have talked about, if you are finding some dislocation, or maybe the pore holes, or maybe the some pores you are getting, or maybe the blocks you are getting inside. So if you will force it, that means if you can squeeze from both the side, that also stress you can relieve. Okay, so there are a lot of the process or the techniques depending on the material you have. And the cold work material is stronger or the harder, but it's brittle. And hitting the material, okay, so this line only you can remember, hitting the material typically below the 0.5 times of the melting temperature is, and holding for sufficient time is a heat treatment process, is known as the annealing. Okay, so for annealing, when we are talking, you have to also think about the different parameter. Also, I have explained you when initially you have to increase the temperature with a certain rate. Then you have to hold it for certain time, and this certain time also you cannot tell that for this material maybe 1 hour, maybe that material will be also 2 hours, or maybe 10 minutes or 15 minutes also you can take. That depends upon the material. Then also the cooling rate, that is also one more important factor, because we are not considering that one in many cases, but you have to consider. If you remember your continuous cooling transformation and TTT diagram, that also you maybe you have learned there, or you have studied there, right? And depending on the temperature of annealing process, like recovery, and the recovery what we discussed in the previous slide at low temperature, and when we are talking about the recrystallization, that means your temperature you was going towards the higher side. And during this process, the material tends to go from a microstructural metastable state to a stable state. Okay, so that means initially when you are squeezing, or when you are expanding your grains, then you are again generating some new grains, then again you are going towards the grain growth. That means your material or your state will be stable there. Okay, normally we are telling equilibrium state, or maybe the stable state. Further, the annealing of the recrystalline material can lead to grain growth. Okay, because you are going from the recovery, then you are going towards the recrystallization, then again you are going to the grain growth. So what will happen when you will make the cold working? So initially you have the annealed material. Okay, so whatever the density you have, then you are from the annealed material. Why you are making? Because you are going towards the stronger material. So that means your the material should be strong, but we are not considering only in that particular zone. After that, what you will get up to the grain growth, or maybe up to the recrystallization, your material will be soft, or your material will be weak, not so hardness will be not so high. But after finishing everything, then automatically your hardness will be increased, right? Is it clear?
Yes.
Okay. Yeah. So this slide also I put in a different way. So when you have the cold work, so what will happen? Your point defect density will increase. Then at the same time also your dislocation density will increase. Okay, so these are just if you can correlate, the point defect, then the line defect, or the dislocation. These are also you can just have a recap of your old the material, what the materials technology you have studied. And then here we have the increase in strength of the material, because if you want to go for cold working, so the final aim will be the strength of material you have to increase. Then you have to go for the annealing, and the moment you are going for the annealing, so your materials tend to lose the stored strain energy. So whatever the strain energy you have inside, so that one you have to remove. That means it will lose there, right? So you have to make the softening of the material. So here also you have the cold work, then you are making the annealing and the recovery and the recrystallization. The recovery normally we are getting at a lower temperature, and the recrystallization we are making at higher temperature. And sometimes also if somebody will ask you, because many when you are working in a heat treatment company, so some materials these are already established, in which technique normally they are following, or normally they are doing. So here I mentioned one or two lines during the cold work, the point defect density, whatever the vacancies, or maybe the interstitial solution, or the interstitial atoms, whatever we have, and the dislocation density. So these are automatically it will increase. And the typical cold working techniques, normally we are following here the rolling, forging, extrusion, and these are also we will study in details in module 3, 4, 5. And the cold working typically done in ductile materials, for example, aluminum, copper, and nickel, etc. Okay, so normally when we are talking about the cold working, so every time I'm focusing on depending upon the material. So also some techniques are established. Okay, you have to do in that. That doesn't mean that you cannot take the same ductile materials to other worm working or somewhere. You can use, but normally preferable this one. If ductile material you have, you can go for the cold working process, right? Okay. Yeah. So yeah, okay, fine. So one more I mentioned here, whenever we are talking about any kind of process, for example, the recovery, then recrystallization, then the grain growth, then what should be the driving force there? Because something is there so that this process is going on. You cannot tell that this automatic, this is going, because whenever we are talking about any mechanical working, we are talking about the forces, because whatever the force you are applying, whether this is forging or whether this is rolling or whether this is extrusion, that is important. Then only you have to find some the outcome. So here also when we have the recovery, so what is should be the driving force? The driving force is the free energy stored in point defects and the dislocation, whatever the free energy inside. So again, you have to correlate with your thermodynamics. Okay, so the entropy, then enthalpy, then the delta G, okay, so the free energy. So that is stored inside the defects, because inside you are getting some defects. Then what is the energy or free energy stored there? That will be the driving force. Then second, when we are going for the recrystallization, so the driving force is the free energy stored in the dislocation. Okay, so you can differentiate here the free energy stored in the point defect, and here this is the point defect and the dislocation. But in recrystallization, this is the free energy stored in the dislocations. And the third one, you have the grain growth, because your grain from a smaller particle or the smaller grain boundary to the larger grain boundary it is going. So the driving force is the free energy stored in the grain boundaries. Okay, because that grain boundary, it was initially small when you have the recrystallization, but the moment it is going towards the grain growth, then your grain boundary, okay, it will increase. So that means the driving force will be the free energy stored in the grain boundary, right? All the three driving force is clear. Okay, so then also some of the parameters or some of the properties also you have to understand when we are making the cold working. What should be the outcome or what we are going to observe there? So the strength will increase, the hardness also will increase, then electrical resistance will increase, wherever the ductility will decrease. These are the parameters we are getting when we are making the cold working process. Okay. Yeah. So the next one we have the recovery. So of course I have said about the recovery initially. So these 2-3 things what I told you, just the background of the the annealing process or the heat treatment process. So the recovery takes place at the low temperature of the annealing. Whenever you are making the annealing at the lower temperature, you are finding the recovery. So there will be no change in the microstructure apparently when we are talking about the recovery initially. If you remember that graph what I shown in the previous slide, and excess point defects created during cold work were absorbed at surface or grain boundary by dislocation climb. So these are again, a lot of things are correlated with the material science and engineering. So just I put a few points there. So if you want to study in detail, then again you have to go for the twinning, then the sleep, then the dislocation defects, point defect, line defect. These are just you have to read again once again. And then the dislocation of same sign arranged into the low energy configuration. So if you want to remember the edge dislocation, these are normally known as the tilt boundaries, and the screw dislocation, these are normally known as the twist boundary. Okay, and the formation of low angle tilt and the twist boundary is termed as the polygonization. Okay, so I'm not going details about the polygonization. So how actually it is making, so just only you can remember here. And the overall reduction in dislocation density is very small here. Okay, and also whatever the recovery we are talking about here, so basically this depend upon the temperature and the time. Okay, so do not only up to now what we have discussed about temperature, but still I am focusing on temperature and time, because within that period also, for example, let's say we are taking the holding time, let's say 1 hour, or maybe the increasing the temperature up to 1 hour. But sometimes if you are considering, I will increase the heating rate maybe 5 degrees C per minute instead of 2 degrees C per minute. So that also will affect to the heat treatment process. So that's why the time is also important when we are comparing with the temperature. So do not exclude the time, right? Is it okay?
Yes, sir.
Okay. Then the next one we have the recrystallization. Okay, so the recrystallization temperature is almost is a set of, okay, the symbol is up to a set of 0.3 to 0.5 times of the melting temperature, and the nucleation and growth of a new strain free crystal you are getting. So that means your particles or your grains, these are nucleating there. So that means it is generating again, and there are the small grains what I shown you. And then again it is going towards the growth side. So that means initially it was very small, but later it developed, then again it grown, right? And the nucleation of new grains in the usual sense may not be present, and grain boundary migrates onto a region of higher dislocation density. Because sometimes whenever we are studying how we will find this kind of mechanism. So let's say you are doing one kind of heat treatment process. Maybe I don't know maybe whether I told you about the phase diagram maybe one time, maybe in composite materials probably, if I am not wrong. So how normally you are telling that, or you are conclude that this recovery and this microstructure you are getting here, and in recrystallization this microstructure you are finding, and in grain growth how you are finding. So how we will do, you have to do the experiment, because the experiment, let's say it is 2 hours. So maybe within 5 minutes you have to stop. Then again you can start, then again after 10 minutes you can stop, or maybe one experiment you can do, so that you will stop there and you will check the microstructure there, or you will check the phases there, so that you will find this kind of structure. Because continuously if you will go to the from beginning to the end, then you will find the initial sample microstructure, then in the final sample microstructure, but in between what is happening you cannot tell. Okay, so you have to stop the experiment in between, maybe after 5 minutes, after 10 minutes, after 30 minutes. Then you can combine all the microstructure together. Then you will find this is happening in this time, this is happening in this time, and this is happening in this time with respect to this temperature, right? So here the free energy or change in free energy of the recrystallization equal to the free energy of the deformed material minus the free energy of the undeformed material. Okay, so these are the thermodynamics when you will study in detail, and then you can understand how we are, because this material also it is related to the thermodynamics. You cannot tell that only the we are getting this kind of microstructure and these are the phases we are getting. So my experiment, I have completed my experiment. No, you have to also correlate the thermodynamics part, or the entropy, or maybe the enthalpy, or maybe the free energy. Then the recrystallization temperature, the temperature at which 50% of the material recrystallizes in 1 hour. So you can see the time is also here is factor. Okay, so these are the the normally or the generalized statement, but depending on the material you have to check. And here I put one schematic diagram here. So this is the region, this side, the right hand side, this is the region of the lower dislocation density. Okay, so these are when this kind of symbol you will find in this dislocation. Okay, whether this is screw dislocation or something. And here actually it is converting to this side. Okay, so these are the region of higher dislocation density. Okay, and it is changing. So that means this direction is from the lower dislocation density to it is going towards the higher dislocation density. Okay, so that means direction of grain boundary migration. So in this direction of the grain boundary, let's say it is showing, so it is moving towards this. So that means you can see we are only thinking, we are just putting the sample, then 2 rolls are there, then maybe we are applying some force, then only the parameters are like, the lubricant or maybe the friction, this kind of parameter. But at the same time, if you want to study the mechanism in detail, because when we are engineers, we have to understand the mechanism, what is going inside. Okay, sometimes, for example, if some mechanism are not clear, so you can tell that these are the proposed mechanism. You cannot tell that these are the exact mechanism, because we have not seen inside what has happened. So you can tell that these are the proposed mechanism, right? Is it clear?
Yes, sir.
Yes.
Okay. Yeah. So I mentioned one more slide of recrystallization. So what is actually happening when we are making the recrystallization? So the deformation, your increase of the deformation, so your recrystallization temperature will go down. Then also the initial grain size, it was lower side or it is decreasing, but the recrystallization temperature also at the same time it is decreasing. Then the high cold work plus the low initial grain size, you will find the finer recrystallization grains. Okay, so these are just I combined whatever I studied, I just combined in one slide, so that maybe you can also recreate something, maybe which part I missed here, maybe some parameters or some property also you can add here. Okay. So one more also I added here, the impurity atoms. Okay, so one more interesting thing is that you cannot tell that only the metal is only one piece or one elemental metal is there. So you will have some impurities there also. Okay, so for that impurity also you have to check the mechanism, how the impurities it will affect to the rolling or maybe to the mechanism when you are checking or when you are going towards the grain growth. So the impurity atoms segregate to the grain boundary and retard their motion. So that means here it will find the the friction also. So that means it will be obstacle there. Okay, so the moment you will find obstacle, so then you have to overcome that one. Okay, so then again you have to check which material is behave to remove that one, or maybe how to overcome that one. For example, when we are going by motorbike, if some the road is, let's say, not good, a lot of mud is there, so then again you have to do something so that you can overcome that road, right? So here it is telling that the solute drag, so it can be used to retain strength of material at high temperature. So whenever you have the impurity, so you cannot compromise the strength there. Okay, so you have to think that how I will do something so that my strength will retain there at a high temperature. If it will again deviate, then again you will face some problem, right? So the second phase particles also pin down the grain boundary during the migration. So what will happen if you have the small grains you have, and when it is going towards the bigger grains, and there is some effect to the grain boundary because you are increasing the grain boundary from the smaller to higher. Okay, so probably there will be some obstacle or maybe some bar there, so you have to overcome that one. Okay, yeah. So the last part we have the grain growth. Okay, so of course normally we know from the smaller particle to bigger particle, but still we should know that how actually it is happening or how it is growing. So the interface in a material cost is the system energy. Okay, inside what is happening. If you remember, we talked about in composite materials three things. One is matrix, one is reinforcement, then one is the interface, right? So here also, if you have the grain boundary, so between two grain boundary also you have to find out how it is contacting there, or how it is touched there. So similarly also you have to understand what should be the system energy inside, and the excess free energy associated with the interface is the interfacial free energy. So if you'll see the curvature driven, I just put one 2D schematic diagram here. If you have the small grain here, so inside the free energy you have, so it will expand or it will grow. So that means it will press inside so that your grain will be little bigger side. Okay, so the moment it will be bigger, then you will find this kind of new grains, or maybe the growth of the grain. Then other the forces you will find the outside. And the grain boundary are the interface between the two crystallites which are differently oriented in the space. The excess free energy associated with the grain boundary is the grain boundary energy. Okay, and the grain boundary energy acts as the driving force. Okay, so this line, the third point, just you can remember here, for the movement of the grain boundary, hence it's a recrystallized material is further annealed, then grains growth take place. Bigger grains grow at the cost of the smaller one. The process is known as the grain growth. Okay, so what I told in the beginning of this slide, that the small particles you have, and then whatever the free energy you have inside, so that one will press inside. Okay, so inside it will stretch, then you will find some bigger grains or the bigger growth. Okay, so that one also, if you want to go for any kind of microscope, or whether this is of high resolution optical microscope, also you can check, but you have to stop some experiment in between so that you can check how the small grains happens now, then how it is going towards the bigger grain. Okay, and one more slide I have also here. In grain growth, actually, what is happening? What are the basic properties? Okay, what you are getting here. So I mentioned here, at any given temperature, there is a maximum grain size at which these two effects are in the equilibrium. Okay, so you have to make it equilibrium. Otherwise, if there is no equilibrium, then you cannot sustain your grain, right? So the grain growth, if it will decrease, for example, okay, all the left-hand side is grain growth. If decreasing, then also at the same time the heating time will decrease. Then the degree of prior deformation will increase. Temperature will increase. Annealing temperature will decrease. Then the insoluble impurities will increase. So if you will see the graph actually, so the x-axis is temperature, okay, and the y-axis is grain size. So if you want to correlate the grain size with respect to the temperature, so you can see here. Okay, so that means initially this grain size will be less, but the moment your temperature is increasing, so your grain size also it will increase step by step. Okay, so this is basic a diagram or the effect of temperature on the recrystallization grain size. Okay, so these are basic some property or some parameter you will find. So you do not think that whenever we are doing any kind of experiment, so we have to think a lot of parameters. We do not think only single parameter that we have to. There are two roles are there, so we can just push the material from left hand side and we will get the product. Okay, because according to your customer demand also, the metallurgical aspect or the mechanical aspect you have to understand as an engineer, but also this depends upon the customer's demand, what actually they need. Okay, sometimes also I asked you if we have some waste product, not waste product, maybe whatever the customer told you, this kind of composition material you have to prepare, but whenever you prepared that material composition little deviate from that, so the customer will not take that one. So some the subsidiary company owner, they will contact you, so you have to give or you have to sell in a cheaper price, right? Is it clear?
Yes.
Okay. Yeah. So this the slide of the summary what we discussed about the recovery, recrystallization, and grain growth. So you can see the properties. So this part is the cold working because we are talking about the cold working, the annealing. So and this is the recovery part, and this is the recrystallization part, and this is the grain growth part. Okay. So you can see, maybe somebody was asking about the internal stress. So you can see here the internal stress how to remove. Okay. So whenever we are making the internal stress in the cold working, so it was higher, and the moment you are going towards the heat treatment or the recovery recrystallization, then of course it is going down. That means you are removing. And similarly, your tensile strength also here it was it is higher side in the recovery and recrystallization part, or maybe half of the recrystallization. Then again it is going down. Okay, so what I discuss about the strength, why it is decreasing. Then similarly, if you have the ductility and the electrical conductivity, okay, so these are also drastically it will go up. Okay, when you have the grain growth. Okay, so these are the basic summary of the the recovery, recrystallization, and grain growth when we are making the cold working. Right? Is it clear? Yeah.
Yes, sir.
Okay. Yeah. So then we have to think about, maybe in the previous class, probably I told maybe one line of the hydrostatic pressure, because many things we are correlating there. Okay, we cannot, and that's why I told that you cannot stick on only one or two parameter or three parameter. So also the pressure also we have to think, or the hydrostatic stress. So I mentioned here the hydrostatic stress is similar to the hydrostatic pressure. Okay, so that's why I mentioned here. And on the element. So if there, one is hydrostatic and another is deviatory. Okay, so the two things we have discussed in maybe one line I have told earlier. So the hydrostatic stress actually is of the principal stress. For example, the sigma h sigma x equal to this stress 1, stress 2 plus stress 3, or the three, and you have to make the average, okay, divided by 3. And these two things you are getting. So one is hydrostatic and second one is a deviatory. So what is the deviatory? So this is the stress remain after you are or after you are stress. So you are getting the deviatory stress, right? And here also, whenever we are making about the hydrostatic stress, this is similar to the hydrostatic pressure. That's why I relate together here. But whenever we are talking about in fluid, this is a different thing. And when we are talking the mechanics of solid, this is different. Last time also we discussed about the EC or the epsilon C. Okay, whenever you have some negative, you have to make it positive. But the moment you are getting the compressive, normally it is considered as negative. So the hydrostatic stress equal to the negative of the hydrostatic pressure, right? Yeah. So one more schematic diagram I just mentioned here when we are talking about the hydrostatic stress or the hydrostatic pressure. So if you will see the schematic diagram here, so you have to also understand the hydrostatic pressure, why the pressure is also important. Okay, so in the left hand side we have the billet, because the billet you are just the die, because you have the die here. Okay, then you are getting the product here, and this is the chamber you have. Okay, with this chamber you have to put the billet here, and inside whenever you are putting here, so that means this side the pressure will be because you can see here this this area or maybe this width is bigger, but the moment you have the less width here, for example the water nozzle, if you will remember. So if we'll put our finger on the tip of the pipe, then the force will automatically increase. So similarly, when you have the, because we have to press it, okay, whether this is two dice are there or whether this is rolls are there, two rolls are there. So you have to push it, and the moment you will push, that means your pressure will be higher in the left hand side, and the moment you are getting the product, there will be no pressure or maybe low pressure, you can say. So as an important factor in achieving the successful forming deformation, because you are operating or you are doing the successful one, you are not doing that maybe whatever I will do, maybe probably it can fail somewhere. But as whenever you are studying anything, you are trying to get more than a 9 CGPA or maybe more than 9.5 CGPA. When we are making any kind of operation, we are telling that it should be success. It should not be stopped somewhere, or it should not be. And the presence of high hydrostatic pressures reduces the tensile stress. So what will happen? You have the high hydrostatic pressures here. So reduce the tensile stress below the critical value for the cracking, while at the same time the flow stress is unaffected. Okay, so already we have discussed about the flow stress and the flow curve and average flow stress. Okay, so similarly also we have to think about this kind of hydrostatic pressure. These are also much more important here when we are and the hydrostatic pressures may arise from the hydrostatic component of the stress state, mainly by the interaction of the workpiece and the tooling, as in the extruder. Okay, so that means how it is actually creating the hydrostatic pressure. You are creating when you have the long width here, then you have the die here. So that means you are creating here. Okay, the hydrostatic pressure you are generating process. The main advantage, the elimination of the large drag friction force between the billet and the container wall. Okay, the billet and the container wall, and the achievement of hydrodynamic lubrication in the die. What we have discussed in the previous class, I put another schematic diagram. So you have the lubricant here. Okay, you have the lubricant here. Then you have the stress generating here. Then you have the friction here. Getting some heat also there because you are pressing there. Okay, so these are the basic advantage. That means you are removing that or you are eliminating that friction force, right? And the hydrostatic pressure may be used to advantage in working the brittle material, for example, the bismuth and the cast iron. Okay, so these are the basic advantage you have studied. What is the basic need of that you studied? Then what are the basic example when you are using this kind of experiment? That also you have studied, right? Is it clear?
Yes.
Okay, so other student become silent, little going ahead.
No, sir.
No, it's fine, nah? Okay.
Yes,
So
sir.
maybe another 2 slide, I think we can stop. Okay. So next one we have, because we have done the mechanics of the forming process. Here just I put more interesting slide that because maybe many students, they are interested about the numerical, because what I observed in the previous semester, many students they got good score. For example, if I will share, maybe I don't know whether your result already declared or not. So in when in machine, the average is very good, because students now, technical students, they are much more worried about the application, because numerical means do not think that only we are giving some data but you have to generate some answer. These are the application part, because how we are for example what we are studying now up to now, because we have to understand how we can apply this one in company, or maybe whatever we have studied, this one is applicable to in an industry or maybe in somewhere. Okay, so that's why we are studying. And also one more thing, we have to understand the mechanism. Okay, whether this is the simulation part, or maybe whether this is mathematical modeling or maybe calculation. So that's why I told in the previous slide, previous class, case everything is covering. Whether if many students, they are much more interested about the simulation, so they can go for the FEL. But some students, they are much more worried about the experiment. The experiment we are doing, and then also how will generate something by my own hand. Okay, simulation is different because you are using in the computer only, but experiment doing by yourself. Maybe some students, I think Charles was trying in the previous semester, about the cutter. If different material, why this cutter is not useful there. Okay, so maybe they have some interest, so they can do. So similarly, I mentioned here the deformation zone geometry, how actually you are getting from in one step, whether this is rolling or whether this is forging, how you are getting. So most deformation process require the material to flow through a converging. Okay, so if you have, for example, if I will take this steps or maybe this sample, let's say, so that means this is your billet you have, or this is your raw material if you have, and these are two dies are there. So you are pressing here, okay, and the basic feature of each channel is the ratio of the min edge, okay, to the length of the deformation zone. So in the last I told about undeformed zone and the deformation zone, which one is going towards the deformed state, so that is known as the deformation zone. So here you can see, so that means the designated this delta equal to h by l. So that means this height and the deformed area or the deformed length, okay, and the delta s is based on the plane strain reduction. Also, whatever the reduction we have talked about, the rs equal to 1 minus h1 minus h0. H1 you will get here, okay, whatever you are getting after the product, after you are getting the final height h1 divided by h0, the initial height, right? And also if you have the w is based on the asymmetric reduction, rw equal to 1 minus d1 divided by d0. Okay, so d1 means if you want to somewhere we are taking this is d1 or the h1, so and this is initial is d0 or h. That the basic things to understand. Then one more good parameter here there, I think probably we have not considered, maybe in machining we have considered up to now, to decrease this this deformation or this delta, we can reduce this semi-die angle alpha. Okay, this die angle. Okay, this angle also. You can just imagine what will, if you will reduce that one, what will happen, and it increase that one, what will happen. Okay, so I mentioned here, if you will reduce the angle alpha, so that means this angle will be lesser, thereby increasing the L. So that means this L, okay, the length or the deformation length is will also R, which decreases H. Okay, so the reduction area or the reduction R also you can increase, whereas your L will increase and the R will increase, so your H will drastically decrease. Okay, so these are the just you can assume something because it will be very difficult to explain you because so otherwise you can probably will find the answer, right? And I put here all the A B C D. So one is the parallel indenter or the plane strain compression, and the B we have this is a drawing or the extrusion, and the third one we have the tube drawing, okay, and the fourth one we have the rolling. Okay, you can see both the roles, and probably we will go in deeply also when we will go to the module 3, right? Yeah. So one more slide. This is the last slide for today's class. So I just put one the comparison. Okay. So dependence upon the yield pressure on the deformation zone geometry for the frictionless. So we are just assuming, because if you have friction again, of course you have friction, but if how we will compare, because with depending upon the material and the techniques, so you have the friction. So we cannot assume that how much friction. Just assuming here this is a frictionless plane strain, how it is relating to the hydrostatic pressure with the okay. So you can see here all the steps we have. Sheet and strip rolling, then this is wear and rod drawing, this is extrusion, this is breakdown, this is heavy forging, this is hardness testing, pursing, and this is hardness testing. So how actually you can see how if you will compare with the here I mentioned the increase in the P by 2K, or that is hydrostatic pressure. P is the tensile yield stress 2K, with the delta is the mainly the result of increasing reductant of the work. So that means in which step, for example, or in which technique, how actually it is changing. Okay, you can see with the different when you are applying for both the area the forces, so you are getting this kind of material. But when you are getting this kind of force and you are finding some next here, okay, and for example when hardness testing all you are finding here. So if you want to, for example, if you have done rolling, if you have done forging, if you have done wear and rod drawing, so you can just compare how this the yield pressure and the hydrostatic pressure, for example, how it is relating. Okay, that's only basic aim of this slide, right? Is it clear? Okay, so I think I need one class. So in that class we will talk about maybe a little bit of residual stress, Then also maybe one factor I remain, I think, workability. Okay, that two things only we will study. Maybe if one more numerical we have, and then also we can do one more numerical or one or two. Okay.